Right, so lecture 27. So finally, we arrived at the last part of the course, and this is the Matroid intersection and union. So here's the question. What is the largest size of a common independent set in two Matroid, M1 and M2? Right, if you have only one Matroid, then the size of largest independent set is just the rank. Right? But if you have two Matroid, M1 and M2, on the same ground set, right? So we want to find the maximum size of I such that I is in the intersection of these independences, right? So this is the goal, and here's an easy bound. So if I is a common independent set of M1 and M2, then rank of I, no, it's not a rank of I is gonna be what can I say? Let's compare I intersection X and I intersection E minus X. Right, so I have set I, and this X is some subset of E. Okay, then I intersection X is independent in the first matroid, so the rank in the first matroid, so let's say R1 is the rank function of the first matroid, and R2 is the rank function of the second matroid. Then I intersection X is independent because subset of independent set is independent. So this thing is equal to I intersection X. This thing is equal to I intersection E minus X. So this is equal, right? That's true. So that means if then the size of a large, okay, so let me say it this way. So this is less than or equal to R1 of X, and this is less than or equal to R2 of E minus X, right? So the size of I is less than or equal to rank of X in the first matroid and rank of the complement in the second matroid. Now let's minimize the right hand side over all subsets. Then this is definitely this, right? So the maximum size of I, where I is a common independent in M1 and M2, is less than or equal to minimum of R1 of X and R2 of E minus X. So this gives an upper bound, and we have seen in the graph theory course, we have seen many min-max theorem where the obvious upper bound becomes the tight. One example was Horst theorem on the size of maximum matching in a bipartite graph, and the other theorem, I mean, we had many, top-Farage formula and Menger's theorem, right? And this is another instance. So the Matroid intersection theorem this was discovered by J. Edmonds. It's the same person in 1970s. That if M1, M2 are two Matroid, so be Matroid with rank functions R1, R2 respectively, then maximum size of independent set is equal to minimum value of rank of the rank of X in the first Matroid plus rank of complement of X in the second Matroid. Okay. Now let me show you the proof. So this direction is trivial. We have seen it already. So what we care is that the other direction. Okay, so we do by induction on number of elements. Okay, and if we have only one element or zero element, then it's trivial. If you have zero element, then empty set is the largest common independent set, and the right hand side is zero. If we have only one element, then right, I mean it's just case checking, right? So empty set is the largest independent set if you don't have any other. I mean if the whole set E is not independent in one of these two Matroid, and then the minimum is zero, so it's easy to check. So the goal is to find a common independent set of size k. Let's say k is equal to the minimum of R1x plus R2x. Okay, that's the goal. Now I'm gonna mimic the proof of Hall's theorem. Remember a long time ago there was some induction proof where you try to find the place where this equality holds. Yeah, so case 1, the I1 plus X plus R2 E minus X is bigger than K for all non-empty and for all these cases. So the equality is satisfied only at the ends, right? Empty set or complement. All right. So we have some redundancy in this case. So what do we do in this case? In this case, let's pick some elements E, and for all X subset of E minus E, what we do is, we observe is the following: R1 X plus R2 E minus E minus X is gonna be at least K. Let's say X is non okay. Oh no, maybe it doesn't matter. Why? Because R1X plus R2E minus Okay, so one reason is R2 minus E minus X is if you compare these two, and what you obtain is the following, right? You lose one by deleting one element from a submodular function. This is because, remember, we know that we have this R2 is submodular, so rank 2 right, we knew this. So when you apply this thing, like if P has size 1, right, something like this. So when you put like E minus X, then it's rank 2 of E minus X minus 1, right? So that's one observation. So if X is non-empty, then I know that this is bigger than K. So that implies that this is at least K. What happens if X is empty? If X is empty, then we use this inequality. R1 of X is R1 of X union E minus 1. It's the same logic. So R1 of X union E plus R2 of E minus X is bigger than K by the assumption. So therefore R1 of X plus R2 of E minus. Oh, yeah. It's at least K. Right? Now, what does that mean? That means by applying the induction hypothesis, to M1 delete E and M2 delete E, we find a common independent set of I of size K in M1 delete E and M2 delete E. But these are independent sets of the initial matroid. Right? When you delete something, the independent sets are preserved, right? The independent sets of the matroid is just an independent set not containing particular elements, so it's okay. So that was each case. So case 2 is different case. So assume that R1x plus R2e minus x is equal to K for some x not equal to empty, not equal to everything. Right? So the claim, we claim that M1 contract X and M2 delete X have a common independent set of size R2 of E minus X. Why? So by induction, if not, then there exists U, which is a subset of E minus X, such that R1 of U plus R, no, okay, R in M1 contract X U plus R M2 delete X U, no, complement is strictly less than R2 of E minus X. So what does that mean? This is R1 of U union X minus R1 of X. This is R2 of E minus U. Okay, it's, let me, all right, let W be, no, I guess it's okay. Can I continue? Yeah, so this means R1 of U union X plus R2 of E minus U is less than R1 of X plus R2 of E minus X. Now, this is equal to K. What is that? That's also partition. It's a partition of E. So that's contradiction. Oh, why is this contradiction? Because the right hand side is supposed to be the minimum. You achieve the even smaller value. All right, so that's contradiction. So thus the claim is true, right? So that let's say I have a independent set. Common independent set of size R2 of E minus X in M1 contract X and M2 delete X. All right. Now, what does that mean? What that means is rank. All right. Now we need to find the. Yeah, we need to find. Okay. Oh, now that's I. By symmetry, there is a common independent set J of size R1 of X in, now the other way around, M1 contract E minus X and M2 delete, no, M1 delete E minus X and M2 contract E minus X, okay? Now what we're gonna do is to say what's happening, right? So here's X, Y, so no, not Y, it's complement. All right, now I is here and J is here. Now let's look at the I union J in M1. Okay, what is the rank of I? Okay, rank of I union J. What is it? And J, okay, maybe I claim, maybe I can just say this. I union J is independent in M1. Why? First of all, I know that J is independent in M1. This is independent in. This means J is independent in M1. Right? And furthermore, rank of J is equal to rank 1 of X. Right. Now, I know that rank 2 I is independent in M1 contract X. So rank of the M1 contract X I is equal to size of I. So rank of I union X minus rank 1 of X, no, not X, X is equal to size of I. But what is rank 1 of X? That's equal to rank that's equal to size of J. So this is I. So rank 1 of I union X is equal to I union J. Now, that is equal to all right, so what does that mean? And I know that this is less than, right? Oh, am I doing all right? What I want to prove is I union J is independent. Now okay, this is not what I want. R1 of I union X plus R1 of J, by applying some modular inequality. Okay, okay, let's say this way. Here is J and here is X. Now if I apply some modular inequality, what we end up is I union X, the intersection is J. Alright, so that now in the group shape. So this is equal to I union J, and this is rank 1 J is equal to J. Actually, it equal to R1 of X. So therefore, the rank of I union J is at least the size of I union J. This implies that I union J is independent. There could be better way, but anyway. And similarly, I union J is independent in M2. And size of I union J is equal to rank 1 of X plus rank 2 of E minus X. So that's K. So that's what we wanted to find. Okay? So the Matroid intersection theorem is proved. Alright. Now by using Matroid intersection theorem, now we're gonna use that answer the second problem. Given n Matroid M1, M2, n on the same ground set E with the rank functions R1, R2, and Rn, what is the largest size of the union of independent sets? So where II is independent in Mi for all I. Right. How do we find the maximum size of union of the independent sets in many matroid? So that's matroid union theorem. Again, there's a E lower bound. How do we get a lower bound? Anyway, let me first state the theorem. This is again due to Edmonds matroid union theorem. So let Mi be a matroid with the rank function Ri for I 1 up to n. Now let I be the union of all, no, okay, let me say okay, take one independent set from each matroid and take a union of them. Then take that set I as a collection. Then not only this largest size is defined, but actually we prove that this thing is a matroid, and its rank function is given by the following formula. That's the theorem. All right. So intersection of two matroids is not necessarily a matroid, but in union of two matroid is matroid. Now let's first prove that M is a matroid. So to prove that M is a matroid, we need to prove I1, I2, I3. But I1 is trivial. Remember, the empty set is in I. That's what we want to prove. I2 is also trivial, because if X is in I, Y is a subset of X, then Y is also in I. That's what we want to prove. So what's left is I3. So suppose that I is a union of II and J is a union of JI, and N size of I is less than size of J. Now we need to find the goal is to find an element in J minus I such that I union that element is independent. Now we may assume that I intersection I J is empty I, right? Because we don't, otherwise just take the subset of II, right? It just, we can keep same I, but if you have a redundant element that belongs to two of the II, then just remove it from others. And Ji intersection Jj is also empty for all I less not equal to J. You may now we choose II and Ji so that something is maximized. I'm gonna decide this quantity later. Okay. And we may assume that I1 is strictly smaller than J1, because otherwise, I mean, it's just by swapping labels, right? You have a 1 up to n, choose the one so that II is less than Ji, and let's call it I1 and J1. Now, there is element E in J1 minus I1 such that I1 union E is independent in M1, right? If E is not in I2 union IN, then we are done. Then I1, then I union E is independent sets. Done. So may assume E is in let's say IK for some k between 2 and n. Now we move E from IK to I1. We keeping the same I, right? Now nothing has changed, right? I is same, J is same. Now what's different? Now the intersection of I1 and J1 is larger. So what I'm going to do is to maximize the intersection of this guy. All right. Now this is contradiction. This contradicts the assumption that the sum of II intersection Ji is chosen to be maxima. Okay, so that's the problem. All right, so now so M is a matroid. Right, so now we need to prove the rank function. Where's the statement? Okay, here's the statement. We are proving the union theorem. Why is this a rank function? Now, to prove the rank formula, it is enough to show it for the case when x is equal to E, because on the right hand side it's all about the Ri, and if x is a subset of E, you just take a minor, right? Delete everything else outside and then you get it. All right, now here's the M1, and here's the M2, here's the M3. Now what we're gonna do is to make a copy of ground set. Right, so let E be the E prime be E times 1, 2, right? So now we have n copies of the ground set. And then let n be a matroid on E prime such that X is independent if it does not contain two elements of the more than two copies of some element in E. So if you okay, let me think of it as a column. Okay, now n is a matroid on E prime where it's independent if it doesn't contain more than one element from the same column. So it's independent if it independent if it contains at most one element from each column. Then it's independent. So that's the one matroid I define. What is second matroid? Let M prime be a matroid on E prime such that X is independent okay, but how do I say? If and only if for all I in 1 up to n, the ith column, ith row of X is independent in Mi, right? Now it's a disjoint union of these elements, right? So it's just a union of one independent set in the first matroid and one independent in the second matroid, one independent in the third matroid, etc. That's independent in M prime. Now we use the matroid intersection theorem to M prime and N. Then what's going to happen? Something is independent. If you find the common independent set, then it contains at most one element from each column, so you don't have any duplicate copies of the same element, and it's a union of distinct rows. So that is actually the largest, one independent set. Now, the size of a largest common independent set of M prime and N is equal to the minimum of M prime X plus rank M N of e minus x, right? Where x is subset of e prime. All right. Now, now I can think of ex as just a collection of n subsets of e, right? So y1 is from first layer, y2 is from second layer, etc. Now, what is rank then? Rank is just sum of the rank of the yi in the ith floor, right? And sum of these rank function is the sum of that is rank of x. What is the rank of e minus x? That is like number of columns it touches, right? So it's e minus number of columns, right? So it's union of e minus yi, right? That's the rank. Now, okay, so let me write it again. First part is good because that's what we want. What about second part? It's minus same as intersection of all yi, right? Now, we are only doing minimum, so we'll be happier if the number is getting smaller. Now, if I replace yi by this intersection, then this part is getting smaller, this is same. So that means I can take all yi to be equal to the intersection of them. So I can just take y to be subset of e, and then sum of the rank. And e minus y. All right. And that is precisely what we have here. Now I think I had a mistake there. Okay, yeah, what mistake? Let me fix the statement. This is x minus y, right? So rank of, and here you have x. All right, so that's it. Okay, so that's the Matroid union theorem. So we have, if you have n Matroid with the rank functions from R1 to Rn, then the union of these independent sets form a matroid, and the rank function is given by this formula. Now, this has many applications in graph theory and combinatorial optimizations, and one of this corollary is follows: matroid, matroid base covering. Or let's start with packing. Okay. Right. So let M be a matroid with the rank function R. Then there exists K disjoint bases of M. What does that mean? When does it happen? Well, it happens if the union of K k copies of M has the rank at least k times rank of M, right? If the union of k copies of the matroid M has rank equal to k times rank of M, then you must have a k back copies, k disjoint bases, which doesn't meet each other, right? So what does that mean? That means the minimum of k copies is at least k copies of a matroid. So yeah, these are the intermediate steps. So therefore we deduce that the condition k times r of y plus e minus y is at least k times rank of e for all y subset of e. So that's matroid packing. Now let's see what happens with the graphs, right? So this is due to Nash Williams in 1961. So let G be a connected graph. And then G has K as disjoint. Spanning trees. When does it happen? Well, let me look at this. So K times rank of Y plus E minus Y is at least K times rank of E for all Y. That's the condition. Right? Now, what is rank of Y? I mean, how do we interpret this? And what is E minus Y? So, all right. So rank of Y is the number of vertices of graph minus number of components, right? So Y could be something like this. It's a component. So Y, then rank of Y is number of vertices, which is fixed constant, minus number of components, let's say S. P1, P2, P3, PS. Right? And then E minus Y is number of edges not in Y. So that is like edges between them and edges inside component. But if you have edges inside the component, then I can include it into Y so that the rank of Y doesn't change. So the E minus Y is getting smaller. So basically, what you end up is you have like components or partitions, right? I mean, you don't have to say partition. Right. But let me say easy parts first. For every partition of Vg into sets P1, P2, PS, where each Pi inducing connected subgraph now left hand side is K times rank, which is K times rank is number of vertices minus S, and number of edges joining distinct PIs is at least K times number of vertices minus 1. Right, that's rank of the whole graph. Now this is same as saying I can cancel this, so what we end up is number of edges joining distinct PIs is at least k times s minus 1. Now, can you simplify it further? If PI doesn't use connected subgraphs, then I can, so there's one case, like if this is P1 but PI, but maybe there's no edge between them, then I can split it into two pieces. If I split it into two pieces, then S is increasing, so right hand side, and that is a good inequality. So if I have a PI which happen to be disconnected and have many components, then right hand side will increase and it will be also satisfied. So I can actually, we don't need this extra condition. So what's left is for every partition of Fuji into sets P1, P2, PS, the number of edges joining distinct PIs is at least k times s minus 1. So that's the theorem. Okay, so this is the if and only if characterization for the graphs to have k as disjoint spanning trees, for connected graph to have k as disjoint spanning trees. Now let me tell you the corollary, and which we used in the previous lecture when we proved the Noether-A flow theorem. If G is 2k edge connected, then G has k as disjoint spanning trees. Why? Let's consider this thing. Let P1 PS be a partition of Fuji and PI is non-empty. Then by the condition number of edges joining PI to V minus PI is at least k, no 2k. So that means the number of edges joining distinct PIs is gonna be k 2k times s divided by 2. So this is at least k times s. Why do I divide by 2? Because each edge is counted twice, one at I, one at j, right? So this implies that there are k as disjoint paths, spanning tree. Right, so if you look at the Diester's book, there is a proof of this Nash-Williams theorem by using pure graph theory, but the proof is somewhat complicated, and there have been attempts to prove it simply. There were, like, I remember that there was one undergraduate student who also wrote a paper on it. So if you were interested, you can try to prove it. Find a new proof using only graph theory. But if you use Matroid theory, then this is easy consequence. And as you see, as long as you know the definition of Matroid and deletions, contractions, then it's straightforward to prove the intersection theorem and union theorem. So it's not that hard. So once you use tools, from Matroid theory, some of the graph theory problems become way easier. All right, so let me tell you another corollary of the Matroid union theorem. So this is called Matroid base covering. So the question is, when can you cover edges by k spanning trees? Right. So let M be a matroid with the rank function R, then M has k bases B1, B2, Bk, whose union is equal to E if and only if. Now, of course, now this should be trivial now. If and only if the sum of the Ry, no, not sum, k times Ry plus E minus Y is at least E for all Y, right? Because we apply Matroid union theorem, so which means the k times Ry is at least Y. So that's the statement. So that's also an interesting observation. All right, so that's it. And this is gonna be the last lecture, so it's over. Thanks for watching all the videos, and I hope you have enjoyed the graph theory and a little bit of Matroid.